Thank you for the invitation. My name is Gaspard Laouenan, and today I will present you a paper written with Paul-Éric Dossou and Jean Delahousse at the ICAM Grand Paris Sud about Flexibilization 4.0 for production manufacturing optimization. Building on the legacy of the three previous industrial revolutions, Industry 4.0 has now introduced a new paradigm where continuous variations of requirements and the versatility of customers have a real impact on the company performance. Thus, enterprises must adapt to produce and offer a broad variety of products, which leads to the need for production stations to become more flexible, which is to say to be able to carry out several processes by keeping high industrial performance. This is of course a big challenge for small and medium enterprises today, and we'll try to focus on this problematic in the paper. In particular, we will present a sustainable digital transformation methodology to solve problems related to human-robot collaboration during the production process, to reduce lead time through tool change optimization, and then we will present the implementation we did in an electronic CAD workshop. Now, the question is, how do we flexibilize a workshop? This will be based on the use of new technologies with the additional adaptability that human resources offer. Indeed, we usually consider that machines can have high pace but limited flexibility, while humans generally have low pace but high flexibility. In addition, on one hand, human-based organization should consider problems such as fatigue, safety and health risks, as well as the need of recognition and the attribution of value-added tasks for operator in exchange of adaptation to new processes, flexibility and skill development. On the other hand, machine-based organization should consider problems such as safety, return on such big investments, of course, and adaptation to new processes, which is not as easy as with humans, but in exchange of automation, higher repeatability and increased availability. This is where Flexibility 4.0 comes into place by combining strength of both in human-machine collaboration. Most cases can be classified as either coexistence situations, where machines and operators don't necessarily interact, cooperation situations, where humans and machines share common operational goals at workstation, and finally collaboration situations where humans and machines are very likely to interact physically. This way, emphasis shall be on safety and attribution of value-added tasks in order for humans to get the more complex and rewarding tasks. Hybrid workstations are thus efficient solutions when flexibility is the main criteria for productions. But how about SMEs where financial breaks are often met? Well, a single flexible tool could perform tasks on several workstations in order to cut down the cost, but the investment alone isn't sufficient, especially if we consider the lead time, because features such as the tool change time, the scheduling of non-simultaneous processes, and the safety and maintenance constraints that come with the investment are very likely to increase the overall lead time, therefore to decrease the industrial performance of the enterprise. In this case, a methodology such as smart manufacturing based on lean manufacturing and the implementation of new technologies is required to optimize those parameters impacting the industrial performance. In our paper, we present and recommend a sustainable framework for SMEs based on lean manufacturing and Gray methodology developed by the University of Bordeaux in the 1980s to model the functioning of a company, as well as the design, measure, analyze, innovate, and control method and the design of experiments. In fact, tools such as Gray methodology or value stream mapping are essential to measure the actual state of the organization with key performance indicators before making any decision. Besides, lean manufacturing, DMAIC combined with design of experiments and any continuous improvement methods such as Plan, Do, Check, Act aim to reduce waste in terms of delays, stocks, breakdowns, travel, movements, complexity, non-quality and overproduction. This way, we designed an intelligent digital transformation tool to support SMEs in their sustainable development strategy by evaluating their current state, defining their desired future state, and finally by getting feedbacks from the implementation of use cases to improve an ideal model of sustainability. In particular, when it comes to the state evaluations, key performance indicators are derived from quality, cost, delay, social, societal, environmental, and degree of modernization criteria, and overall the assumption that the framework is willing to test is the idea that implementing Industry 4.0 concepts and smart manufacturing method as a solution to human needs will increase industrial performance for SMEs in a sustainable manner. For example, the need to reduce energy consumption can be performed with IoT and big data in predictive maintenance use cases to reduce breakdowns. Transferring responsibilities of operators by automating arduous and non-value-added tasks can reduce human accidents and unavailability caused by health risks. Digital twins can avoid useless complexity in processes before physical implementation and therefore make cognitive resources available for rewarding and value-added tasks. In this paper, we focused on flexibilization of human-machine collaboration to measure reduction of wastes in terms of delays, accidents, unused cognitive resources through use cases with an electronic company. This translates into having a cobot that will operate several processes on different workstations. Thus, single-minute exchange of die and value stream mapping are useful methods to identify the value-added parts in the process and optimize the overall lead time. In the end, flexibilizing such a tool has to be done by integrating an ergonomic process control UI to ensure acceptability and to reduce complexity of the system. Moreover, this flexibilization use case implied the design of a trolley for interstation transfer to be performed by either an operator or an autonomous mobile robot. The sizing of a cobot includes safety, operating tool, artificial vision, and other sensors. Keep in mind that accessories must be sized to ensure interoperability between workstation and the mobile cobot. Thus, camera use cases are limited by cobot's degrees of freedom. For example, bin picking with a 3D camera requires the use of at least a 6-axis robot. Cobot's payload and reach must be greater than the maximum required load and reach. However, when it comes to operating tools and sensors, different needs might not be handled by the same single tool. Indeed, there is no order relation on a functional level between a gripper and a soldering iron. This implies that tool changes for the cobot shall be considered. In our case, we work on pick-and-place use cases that require electric and pneumatic grippers. This is why the design of the trolley must consider the electrical and pneumatic supply of its components, as well as the means of communications with the workstations. Especially if the supply is provided by a storage system at the workstation, stability of the trolley becomes essential. Thus, 3 approaches have been considered. One with electromagnets, another one with electric cylinders, and a final one with a lock. Among those, we focused on a solution with 4 electric cylinders. So you can see here the layout we chose to perform the stabilization. If you wonder why there is a gap in front of the trolley, this is for safety purposes because the AMR that operates the interstation transfer is using frontal laser scanner for pathfinding and detection. Besides, having an electrical stabilization systems allows us to integrate their automation in the MES that also runs the AMR fleet and the workstations. For this, we used a Raspberry Pi 4 to drive the cylinders through a web server application. Although in the end, the use of cylinders meets breaks because of low frequency vibrations caused by the working process of the cobot or by potential collisions during the process. The main issue being that the cylinders are not the best solution to ensure stability in relation to the workstations. Here you can witness the gripping of the trolley with the AMR. One thing to notice is that the time taken by the AMR depends on the surface quality of the ground, because scratches and stains can be interpreted as obstacles by the program. This might be considered as break to overcome in the evaluation of the current states for the SMEs, but for example, the 5S method gives solutions to deal with this kind of problem. Here you can see the temporary UI we developed to control the stabilization system with the web server application on the Raspberry Pi 4. Full automation of the process was then carried out with the integration of an API. At the end of the day, the overall tool change time with automated transport of the trolley depends on the stopping of the process and the arrival of the AMR, the pickup of the trolley by the AMR, the turning off of the stabilization system, then the travel to the assembly station to change the accessories for the next process and the travel to the next workstation. However, this part of the process can be greatly reduced with the use of quick tool changers depending on whether or not the required operating tools can be embedded on the trolley and powered. For the few ones that can't, the inter-station transfer process is flexible enough to ensure the tool change on an isolated assembly station. For the rest, there is a storage at the next workstation with the turning on of the stabilization system, the departure of the AMR, and the starting of the next process. Next steps about the use cases of the trolley include the test of the other stabilization systems. In fact, the Vero-S tool changer system developed by Schunk have later been tested as a lock to ensure stability and safety while using the trolley. With the company now, they are currently preparing the establishment on a new site that will integrate the use cases studied here to improve the industrial performance. Future states of the company will be checked to test the hypothesis about the framework. And now, in a more global view, a demonstrator in Industry 4.0 is being implemented at the ICAM Grand Paris Sud. The demonstrator will include production lines for electronic cards and small robots and will implement Industry 4.0 concepts and the sustainable methodology.